Hello, and welcome to another video where I'm explaining the four main ingredients for severe weather and where they come from. Last time I talked about lift, which is a trigger mechanism for thunderstorms, and in this episode we're going to talk about moisture. What role does moisture play in severe weather? Moisture serves as the fuel for stronger thunderstorms, as deep convection will favor the higher moisture content. I'll discuss the different air masses and their moisture characteristics. And in this image you see here, this comes from weather.gov/jetstream, and it's just showing where some of our moisture sources come from. And I'll talk more about that here in just a moment. And then we'll discuss the mass response and how that occurs. And then after that, we'll discuss how we quantify moisture. So if you enjoy this video, leave a like and subscribe, and we'll get started. There are 5 types of air masses that characterize temperature and moisture, and those are continental, maritime, polar, tropical, and the Arctic. 3 of these describe temperature, which are polar, tropical, and Arctic. The other 2 will be continental and maritime, which characterize moisture. So the source regions for these air masses are pretty intuitive, and I'll run through them real quick. And also, what I've outlined here, this is just the source region for these different types of air masses. Oftentimes, these air masses will extend well beyond just where they come from. So first we have the continental polar air mass, which is abbreviated as CP, and that is a cold, dry air mass that originates from usually the northern interior of the United States, so from the northern Rockies over through the northern high plains and sometimes into the upper Midwest. And then we have the continental tropical air mass, abbreviated as CT, which is a hot and dry air mass that originates from the desert southwest and into northern Mexico. And this also plays an important role for severe weather. When this air mass is moved over into a target region where we're forecasting for severe weather, that can influence the severe weather threat. And we'll talk more about that in the next video where we talk about thermodynamics. And then next we have maritime polar, which is abbreviated as MP, which is a cool and wet air mass. And this air mass has two different source regions, one over the Pacific Northwest, over Washington State and Oregon, and then another source over the Northeast Atlantic coast. And then we have the maritime tropical air mass, which is a warm and wet air mass that originates over the Gulf of Mexico. And then we have the Arctic air mass, which originates over the Arctic Circle. And I don't have it, so this is just over the map of the United States, and so I don't have the Arctic air mass outlined, but it originates over the Arctic Circle, and occasionally this will come down into the United States in some of our bigger Arctic outbreaks. Recall back to last Christmas where it was extremely cold. That's an example of an Arctic air mass that comes all the way down to the United States. The maritime tropical air mass has the highest moisture content and therefore is most favorable for thunderstorms. The maritime tropical air mass is most prevalent in the southeastern U.S. due to the close proximity to the source. But this air mass will still need to be pulled northward in order for thunderstorms to be favored. So how does this maritime tropical air mass return to the United States? This is the result from the mass response, or also known as the moisture return. So remember back in the last episode where we talked about advection. And if we recall, advection is the transporting of atmospheric properties from higher to lower quantity. And we talked about 2 types of advection, temperature advection and vorticity advection. And now we're going to talk about moisture advection. So how does moisture advection occur? It starts with your mid-latitude cyclone that develops east of the Rockies. And so this is basically your low pressure system. And here's your frontal system, just for an example. And then that's going to, the result from the developing low pressure system east of the Rockies is going to shift the surface winds to the south. And that's going to pull the moisture moisture from the south. That's basically your maritime tropical air mass. And so that's what's known as the mass response. And so there's one more feature that initiates moisture advection, and that's going to be the low-level jet. Recall in the last video where I talked about the jet stream. The jet stream is a river of stronger winds aloft. When this jet stream moves across the Rockies, a low-level cyclone develops around 1 or 2 kilometers off the surface at 850 millibars. And that cyclone is going to generate strong southerly winds on the east side of it. And this right here is what's called a low-level jet, and that's where the low-level jet is located. The low-level jet is crucial in forecasting severe weather because it plays two main roles. The first role is it transports heat and moisture. So that's your temperature and your moisture advection. And it also increases the low-level wind shear as well, which will be talked about in a different video. So how do we quantify moisture? There are a few different ways that we can measure moisture, and the most common way is what we call the dew point temperature. Dew point is defined as the point temperature has to be cooled to in order to reach saturation. So for those of you who have never heard of dew point before, you can kind of think of this as the saturation point. Along with the low-level jet, dew points are crucial in severe weather forecasting and are mentioned all the time in these forecasts. The higher the dew point, the more moisture there is on that level, and generally, the greater the storm potential will be. So what's another way that we can measure moisture? The next method to discuss is called the mixing ratio. And I'll define that here for you real quick. And in meteorology, the mixing ratio is the mass of water vapor compared with the mass of dry air. And it is measured in grams per kilogram. So I'll illustrate what we're talking about here. So let's assume we have a kilogram of dry air here in this circle. What we're measuring here is the grams of water vapor that we have inside this kilogram of dry air. And so these water vapor molecules are mixed in with that dry air. And so that is why we call it the mixing ratio. So it's grams of water vapor per kilogram of dry air, essentially. And knowing the mixing ratio is important because it impacts on how quickly condensation happens and how quickly clouds will form. And I'll go ahead and briefly introduce that term. And so the term that we use to describe that is called the LCL, which stands for lifted condensation level. And so that's basically the level at which condensation occurs. And we'll talk more about this condensation in the next video on thermodynamics. I'll show you what the mixing ratio lines look like on a skew T. So you can find your mixing ratio on a skew T, and these lines are dashed lines that go from the bottom left to the top right. And these are, again, measured in grams per kilogram. Now, to recap what we've talked about, we talked about the different air masses and their source regions. We discussed the mass response, which leads to moisture advection. This occurs by the development of the mid-latitude cyclone and the low-level jet. I introduced ways that we quantify moisture, and now that we've learned all of that, let's look at our case study and try and apply what we've learned here. So we're using March 31st as a case study for this series. And I'm going to point out some features that we have here. This is 2 days before the event, and here is your surface low over here in Utah. And we have your trough axis that's sitting back out here in California. And then we have our maritime tropical air mass that I'll outline for you here that originates in the Gulf of Mexico. And so we're going to watch this maritime tropical air mass be pulled to the north ahead of this storm system. So this is 2 days before the event. Let's go forward 24 hours to the evening beforehand. And you can see here, I'll point out, here is your surface low over here in eastern Colorado. So it's east of the Rockies now. And your surface winds down in the southern and central plains have shifted to the south. and that is pulling your maritime tropical air mass to the north. And I'll kind of outline where that is now. Characterized by dew points in the mid to upper 50s at least, and you have low 60 dew points that's coming all the way up into Oklahoma. So the moisture is returning very fast. And so we're going to watch the progression of our moisture. We're going to go forward 12 hours. We're going to go to sunrise that morning on the 31st. So here is our low pressure system that is now tracking over Nebraska and Iowa. And you see how fast that moisture is being pulled north. Look at your 60-degree dew points. That's going all the way up to Kansas City, Missouri. And so here is your maritime tropical air mass, which is also considered our warm sector, which is just a sector of your mid-latitude cyclone that is characterized with warm and moist air, basically. And so this is a very pristine warm sector that is being pulled to the north ahead of this mid-latitude cyclone. And so we're going to watch the progression here. We're going to keep progressing to the middle of the afternoon to about 4 p.m. And so this is where the peak of the event was basically at. And so here is your low pressure system over Iowa. And you even have mid to upper 60 dew points being transported through the lower Mississippi Valley. And then you have low 60 dew points that is all the way through the deep south and into the Midwestern region. So that was how the moisture and surface moisture was transported. So let's discuss the low-level jet. What was the low-level jet like on that day? Well, here is the position of your low-level jet. Generally about 40 to 50, even 60 knots in some places. Over here in the eastern plains, over the Ozarks, lower Mississippi Valley, all the way up into the Midwestern region. You have a strong southwesterly low-level jet between 40 and 60 knots. And so this is also responsible for initiating that moisture return and also added to the low-level wind shear. And that's kind of why this event was such a prolific outbreak. Kind of remind ourselves here. This was the storm reports from that day, and one of the largest outbreaks that we've seen in quite some time over the past years. So that's going to wrap it up for this video, and I'll see you in the next video.